Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be introducing this concept called equilibrium. Now, when people hear this idea of equilibrium, a lot of times they end up going to this first bullet point, and that is when equilibrium is established, that all the concentrations are equal to each other, and that is not true. So this does not mean that the concentrations are going to be equal at the end. What it does mean, okay, is that the forward rate and the reverse rate are going to be equal to each other. And the example that I'm using is a very simple A reacting to form B, and it's in equilibrium, which means A reacts to form B and B forms to react A. Now, what happens initially, if you have all of one and nothing of the other, is there's this first phase that's called a shift, okay? And then after the shift occurs, then the forward rate and the reverse rate become equal to each other and equilibrium is established. So let's take a look at our first graph, and this is just a simple example to kind of go over the basics of equilibrium. So let's say I have this chemical reaction, and in the first graph, I have a whole bunch of A and absolutely nothing of B, okay? Well, what I do know is that in order to achieve equilibrium, I at least have to have some amount of B. So that this reaction, the forward rate, okay, is going to be faster than the reverse rate initially, okay? So what's going to happen is something like this, okay? That A is going to come down in concentration, and then it's going to level off. And then the B, okay, if this is decreasing in concentration, that means it's reacting this direction faster than it's reacting in the reverse direction. So if A is reacting, that means it's producing a certain amount of B. So if this reacts fast initially, then this is produced fast initially, and then as it levels off, this one should level off as well, okay? So there's two parts of this graph, okay? And I'm going to draw kind of like a dotted line, kind of like right there, okay? On the left-hand side of this line is where the reaction is shifting. And that means when it's shifting, that means one rate is faster than the other rate. And based on this shift and seeing that the A is being consumed and the B is being produced, to me, I'm saying this is shifting to the right, okay? And then after a certain amount of time, the concentrations are no longer changing. And that's when we say that this thing is at equilibrium, okay? So it's not at equilibrium until this time t exists and the concentrations stay the same. Now, the reason why the concentrations remain constant is because after this point, okay, the forward rate and the reverse rate, they're equal to each other. So as fast as we can make B, B is making A. And if those rates are exactly the same, then we would not expect a change in concentration and that they would remain the same. Now, as you can see, okay, there is more A than B. The concentrations are not the same when equilibrium is established. Once again, the only thing that is the same or what is equal to each other is the rate of reaction going forward and backwards. They're the same, and therefore the concentrations stay constant, okay? And then we end up having this balance of reactants and products, okay, in a chemical reaction. And that value for that balance of reactants and products will remain constant no matter if you start out with a whole bunch of A or if you start out with a whole bunch of B, okay? Now, in this second reaction, okay, it's the same one that occurred before, okay? And the only difference is instead of starting out with all A, we're starting out with all B. So we're starting on this side, okay? And what some students tend to think is that you're going to end up, having a graph that looks similar to this one, and you're not, okay? What's going to end up taking place is that they're going to end up getting to the same balance of reactants and products, and that's what equilibrium's kind of going to be at. So this one kind of ended at this level, okay? So what we're going to do is we're going to end up seeing something that looks like this for the A. You can see how much it's being produced, and that's because it's shifting to the left to make all of this A. So that means the B is going down in an equal kind of like magnitude, and then it levels out. And to me, it looks like equilibrium is established somewhere around here where the concentrations are staying constant. And what I try to do is I tried to line up the A in the B perfectly. I don't know if I did a perfect job of doing that, but over here is where the shifting is occurring. And then this is where equilibrium is established. Okay. The thing that I want to point out to you is that it doesn't matter if we start with all A or all B. In the end, we're going to have, in this reaction, more A than B. Okay, so you can see that the blue line of the A, okay, and I'll just kind of remind you here, is much higher than my B. And just to make sure you understand this concept fully, okay, what would happen if we started out with equal concentrations of A and B? Okay, hopefully you would say that the B would increase and that the B would decrease. So once again, we end up at those same kind of balance of reactants and products. Okay, it looks like equilibrium is established somewhere around here. So this is where the shifting is occurring, and then this is where we have it at equilibrium. Okay, so doesn't matter if you start out with all A, all B, or a balance of A and B. For this particular reaction, okay, you're going to end up having a little bit more A than B. Okay, their concentrations are not the same, but the balance, okay, of the reactants versus the products will kind of be kind of the same ratio. Okay, and we have kind of an expression and an equilibrium constant that talks about this ratio of A to B. And we call that the equilibrium expression. Okay, so I have this generic equation over here, which is A plus B yields C plus D, where the lowercase letters, okay, are the coefficients of the balanced chemical equation. So to find the equilibrium constant, okay, it ends up being the products, C and D, over the reactants, A and B, where the coefficients, which are the lowercase letters, are the exponents. Now, a couple things that we need to talk about here, okay? Number one, that this little c stands for concentration, and that's why these are in brackets, because brackets represent concentration. More specifically, they represent molarity, which is a type of concentration. And if we get a K value that is much larger than 1, what that means is that our numerator is larger than our denominator by a lot, and therefore it's going to favor the products. So when you have a K value that's a large number, like 99,999, something like that, that means that your numerator is going to be much larger than your denominator, and that's going to favor the product side. Okay. Now, if we did the exact opposite idea, if we had a number that is much less than 1, okay, through this expression, okay, well, how do you get a small K value? Well, that's by having your denominator being much larger than your numerator. And if my denominator is much larger than my numerator, then I'm going to get a small K value, okay? And if that denominator is larger, okay, that means it's going to favor the reactant side. So when we look over here at this equation where it looks like there's more A than B, okay, well, if we were to write this equilibrium expression, it would be the products over the reactants, okay, and since they both have a coefficient of 1, the exponents would be 1, okay, but it looks to me like I got a lot more A than B. I'm just going to throw in some random numbers, okay. What happens if I say, okay, The A here is equal to 8, okay? And then the B here is only a value of 2, okay? Well, if I go in my calculator and hit 2 divided by 8, okay, I'm going to get this value of 0.25, right? Which is a number that is smaller than 1, okay? Which means it favors the reactants, which means that there's going to be more A than B, okay? And this is kind of like the basics of equilibrium, okay? Now, I just use this generic equation of A and B. Let's get into an actual example of a real chemical equation. And I want to see if, number one, can you write what we call the equilibrium expression, and then can you calculate its value, kind of like what I did up here. Okay, so let's go ahead and get into a real chemical equation. Okay, and the chemical equation I'm going to deal with is NH3 with N2 and H2. So let me just kind of erase these stray marks here very quickly. And let's say I had the following equation, okay? So let's say I had some NH3, and it's going to be in equilibrium with the N2 and H2, okay? And this reaction is taking place, okay, at a particular temperature, okay? And the temperature that we're going to work with is 472 degrees Celsius, because the K value, okay, is dependent on the reaction and the temperature. So every chemical reaction will have a specific K value for that reaction at a particular temperature. So I'd like you to pause the video right now, and I'd like to see if you can write what we call the equilibrium expression, okay? And I'd like you to do that for this equation. When you unpause the video, I'll be working the problem out, okay? So Kc value here, once again, it's the products over the reactants. So my products are the N2 and the H2, and that's over the reactants, which is going to be NH3, and the exponents are the coefficients in the balanced chemical equation. So this is the equilibrium expression for this particular chemical equation, okay? Now, I'm going to do a what if, okay? What if we have this chemical reaction that takes place, we allow it to shift and achieve equilibrium. And at equilibrium, we discover it has the following concentrations, okay? That the concentration of the H2 is equal to 0.1207 molarity. The N2 has a concentration of 0.0402 molarity, and the NH3 has a concentration of 0.00272 molarity. Now, even before you begin, okay, the thing that has the lowest concentration, okay, is going to be the NH3. So it seems like there's more N2 and H2 versus the NH3 when this has achieved equilibrium. So maybe we can predict that this equilibrium constant is going to be a number larger than 1, okay? But let's go ahead and plug the numbers in to double check, okay? So we're going to plug in the N2, okay, which is 0.0402, and that's going to be to the first power. The H2 is 0.1207, and that's going to be to the third power. And this is going to be all over 0.00272, and that's going to be to the second power, okay? So we're going to plug that into our calculators, okay? So here we go. We got 0.0402. Let's try that again. 0.0402 times 0.1207 to the third power, right? To the third power, and that's going to be divided by 0.00272 to the second power. And we get this number of 9.55. Well, 9.55 sounds like a number that is larger than 1. That means it's going to favor the products, which means the N2 and the H2. are going to be larger than the balance of the NH3. And that's exactly what's kind of taken place with this particular equation. Okay, so I'm going to kind of erase this stuff over here and then talk about, well, what happens if we reverse this reaction. Okay, let's say we write it this way: N2 plus 3H2 is in equilibrium with 2NH3 at 472 degrees Celsius. Okay, well, what is the Kc value for this equation? Well, remember, it's going to try to achieve the same type of equilibrium. Okay, so the N2 and H2 are going to be in larger concentrations than the NH3. Okay, and we can plug these numbers in the calculator. Okay, and we're going to end up getting a different number because the N2 and H2 are now on the left-hand side, which means that the reactants and the products have been flipped. So what's in the numerator and denominator has flipped as well. For example, the equilibrium expression is going to look something like this: the products over the reactants, where the coefficients are the exponents. So this number is now up here, okay, and these numbers are now down below, okay? And when you plug everything in, you're going to get 0.105, okay? Well, 0.105 is a small number, okay? But remember, small numbers are going to favor the reactants, and the reactants that are being favored are the N2 and the H2, the same way as this is a large number and it favors the products, but it's still favoring the N2 and the H2, okay? So I guess what I'm trying to say is that if you reverse the reaction, the products become the reactants become the products, so those things get reversed. So if you end up having a big number over here, okay, you better end up with a small number over here because the chemicals have switched sides, okay, and we need to make sure that we're still favoring the N2 and H2 for this problem, okay? Now, what happens if you are taking a test, okay, and they don't give you these equilibrium values, okay, but they give you the equilibrium constant for this reaction, okay? And then they ask, hey, how do you get to this 0.105? How do you find out the equilibrium constant for this reaction, okay? Well, what you do is just say, well, if I'm reversing the chemical reaction, that means that we're flip-flopping our reactants and products, and simply I'm going to have the inverse, okay, of whatever I had before. And that too is going to come out to be the 0.105 answer. Okay, so what should you have learned from this video? Number one, can you write the equilibrium expression given a particular equation? Do you understand that when things are in equilibrium, it does not mean that things are equal concentrations, okay? And therefore, after you plug these numbers into your equilibrium expression, can you evaluate this number, okay? If the number is large, it means it favors the products, in this case, N2 and H2, okay? For the reverse reaction, okay, if the number is small, it's going to favor the reactants, which is still the N2 and the H2, okay? In our next video, we're going to talk about how we change this Kc value, okay? How we're going to change it into something that's called K sub P. So watch the next video if you're interested in learning more about equilibrium. Please like and subscribe. When you leave that comment, it does push this information out to other students that are interested in learning chemistry.